Dimensions of a physical quantity are the powers to which the fundamental quantities are raised in order to represent that physical quantity. In other words, by the dimension of a physical quantity, we mean the way it is related to the fundamental quantities. We have 7 fundamental physical quantities. These are length, mass, time, thermodynamic temperature, electric current, luminous intensity, and amount of substance. We already know SI units for these fundamental physical quantities. Symbols representing the dimensions of these fundamental quantities are shown in the table. Let us try to understand the concept of dimensions first with the help of an illustration. Consider a point that can move along a straight line. To locate the position of the point at any instant, we need only one information. That is, how far the point has traveled from its starting point. We can see the situation remains the same even if we choose a vertical line instead of a horizontal line. If we consider both the axes simultaneously and try to discuss the particle motion, then we can also understand when the particle is moving along the horizontal line, it does not move along the vertical axis. These horizontal and vertical axes are independent of each other, so they can be considered as fundamental quantities and can act as the base in the dimensional analysis. Using this axis, we can locate any point in the plane. This is how fundamental units help to express derived units. Dimensions of a derived quantity contain information related to more than one fundamental units. Based on the dimension of physical quantities, they can be classified into 4 categories. These are dimensional constant, like universal gravitational constant, Planck's constant, Boltzmann constant, speed of light, etc. Then we have the dimensionless constant like various numerical values, pi, e, etc. At next, we have dimensional variables. Most of the physical quantities generally fall in this category, like displacement, acceleration, force, time, etc. Finally, dimensionless variables like specific gravity, strain, angle, etc. Now let's see the dimension of fundamental physical quantities once again. The dimension of length represented by capital L, mass is represented by capital M, time is represented by capital T, thermodynamic temperature is represented by capital K or theta, electric current is represented by capital A or capital I, luminous intensity is represented by small cd, and amount of substance is represented by small mol. We must remember that these quantities are independent of each other, hence they can act as the base in dimensional analysis. We need to remember the following points related to dimensions. All derived physical quantities can be expressed in terms of 7 fundamental physical quantities. This notion we have already discussed with the illustration of mutually perpendicular axes set on a plane. The mathematical expression of a physical quantity may be different in different cases, but the dimensions remain the same. Dimensions of a physical quantity are independent of the system of units used. Now let us discuss how to represent dimensions. Considering the dimensions of a physical quantity Q is A in mass, B in length, and C in time, we can express it in the following manner. Q equal to m to the power A, L to the power B, T to the power C in brackets. Remember, dimensions are the powers to which fundamental units are raised. If we take the example of force, it is having dimensions 1 in mass, 1 in length, and -2 in time. Hence, dimensions of force can be expressed as mlt to the power -2. This expression is called the dimensional formula. If we replace the dimensional formula of each physical parameter into an equation, then it is called a dimensional equation. Now let us introduce the principle of homogeneity. According to this principle, physical relation is dimensionally correct if the dimensions of the fundamental quantities are the same in each and every term of either side of the equation. This principle is based on the fact that only quantities of the same kind or dimensions can be added or subtracted. Consider the following physical relation s equal to ut plus half at square, where s is the distance traveled by car having initial velocity u and acceleration a in time t. If we find the dimensions of each of the terms, then we can find out the dimension of the left hand side are the same on the right hand side. If a physical relation is not dimensionally homogeneous, then the equation is incorrect. Let's see another example of dimensional homogeneity. Considering the relation fs equal to half mv square minus half mu square, if we evaluate the dimensions of the left hand side and both the terms on the right hand side, then we can see it follows dimensional homogeneity. Now let us see some applications of dimensional analysis. We can use dimensional analysis to derive a physical relation. If we can estimate the factors upon which a given physical quantity depends, then we can find the relation between the physical quantity of the factors. To elaborate, let us obtain an expression of the time period of a simple pendulum. The factors may affect the time period of a simple pendulum are mass of the bob, length of the string, and the acceleration due to gravity. We consider a dimensional expression of the time period of the pendulum and evaluate the powers to form the expression. However, we cannot find the constant factor appearing into the final expression. We know its value is 2 pi, which can be found from experimental analysis. We can use dimensional analysis for the conversion of units of a physical quantity. The magnitude of a physical quantity remains the same irrespective of the system of units. Suppose we have a physical quantity q and n1 and n2 are its numerical value in system of units u1 and u2 respectively. Clearly q equal to n1 u1 equal to n2 u2. Now if the dimensional formula of the quantity q equal to m to the power a, l to the power b, t to the power c in brackets, then we can express the quantity in the first system of unit as n1 times m1 to the power a, l1 to the power b, t1 to the power c, and in the second unit system as n2 times m2 to the power a, l2 to the power b, t2 to the power c. Equating these two, we can obtain the conversion relation. We can use dimensional analysis to evaluate the dimensions of constants. Here, as an example, we have evaluated the dimensions of the universal gravitational constant from the laws of gravitation. Dimensional analysis is very much helpful. However, it is having various drawbacks too. Its limitations are as follows. We cannot find the value of a constant. As an example, we can consider the time period evaluation of a simple pendulum. If a physical quantity depends on more than three factors, then establishing a relationship among them becomes very difficult. Equations containing terms like trigonometric, exponential, logarithmic cannot be analyzed because these factors are dimensionally independent. We cannot tell whether a physical quantity is a scalar or vector based on dimensional analysis. We cannot use dimensional analysis to derive a physical relation containing more than one term. Yes, we can check the dimensional correctness using homogeneity, but we cannot be sure with the exact form of the equation.